So RE helps you in this case. And then R out for this device. We said, okay, so with this device here, if I attach my test source to the output, over here I have a current source, which is not affected by that test source. So then looking back, that current source, because it's a dependent current source, will be 0. And I only see RC at the top, to ground, right? Because small signals, VCC will be ground. And this is if we ignore the early effect. If you don't ignore the early effect, it's a little bit more complicated. You have a small signal resistance between the collector and emitter. For this course, for what you normally deal with, don't worry about it, this is good enough. Now, I just want to do one more thing here before we move on and analyze the full circuit. I want to look at this gain formula for a moment. So AV is minus GM RC. So that's the intrinsic gain of a common emitter state. This is the maximum gain you can get from a common emitter state. How do I get that? You either don't put RE in your circuit, which is a bad idea, because this RE will stabilize your bias point if you like that, or you bypass it. So you include it, but you put a capacitor next to it to get rid of it for AC performance. So you can set RE to 0 and still have a stable bias point. And we also analyze this circuit from large signal point of view, right? So what I write here is not new. But for GM, you can write IC over VT, and this is times RC. Somebody here tell me, what is ICRC?
V out?
This is the voltage drop.
Yeah, so it's V out.
No, it's not V out. V out is VCC minus ICRC. ICRC is the voltage drop across your collector current, the collector resistor, right? So the DC voltage drop across your collector resistor determines your gain. The higher that voltage drop, the higher your gain, right? Because this 1 over VT is almost 40. So the higher that voltage drop, the higher each volt of voltage drop across RC give you a gain of 40, more or less, okay? And then for that reason, you can see that if I have to have, or if I'd like to have a high gain amplifier, I would put VC close to 0, close to emitter, as close as possible to emitter. Why? Because I want to have a lot of DC voltage drop across that RC. It takes away my swing though, right? It eats my swing. Because then if I drop the collector voltage a tiny bit, I enter saturation. So I do that if I know the signal at the output is still small and I want to have the maximum gain. There was a question here.
So, sorry, just that equation is just for maximum.
This is the intrinsic gain. This one, you mean?
Yeah, that's like not factoring in RE.
Well, it's assuming RE is 0. That's the
Yeah.
maximum gain you can get. So this is called the intrinsic gain. The maximum potential gain you can get. Okay? So this is so this is the reason that a high gain amplifier may not have a lot of swing, because you have to put that collector voltage close to 0. And then another point to remember forever is that if you can do a job with 2 amplifiers instead of 3, do it with 2. Not because of cost, not because of all these other problems. Your life will be so much easier. Your performance will also probably be better, especially when you look into considerations like noise. So use the minimum number of stages that you can. If you can do it with 1, do it with 1. Some usually you can. As we saw, we love this stage. It has a large input, it has a large gain, a large input resistance, but the output resistance kind of sucks. So we cannot really live with just this one stage. Usually you have to have more than one. But use the minimum number of stages whenever you can. Okay, so we know this stage, right? So we figured all of these through small signal analysis. And now let's look at the proper circuit. Right? So this is the type of question you may see. What is the gain of this circuit? So this is a common emitter amplifier. You should be able to recognize what's happening here. Look at your signal. The signal is coming from here, goes into the base. Where does it come out? The collector. So this is the common emitter stage. Right? I have bypassed a portion of RE, kept some of it, The biasing through your H biasing network, we've seen it before. Your input source may have some output resistance, 10K, whatever, input is 10K. And the load is represented by a 10K resistor. That load may be a second amplifier stage, or it could be a speaker, or it could be something else. So it's representing what needs you're saying. It may or may not be a resistor. It could be an oscilloscope probe, right? From what we are considering. And then notice that I'm using relatively large capacitors, 1 microfarad, to bypass this resistor or couple the source to my input or the load to the output. If I don't use the capacitor as the input, for example, let's just see what happens. If I don't use C2, the DC voltage from my source is going to affect the DC bias point of my circuit. I don't like that because I do not control the source side. It may be some random DC voltage. At the output, if I don't put C3 there, if I change my load, it can affect the operating point of my transistor as well. Remember, operating point has 2 parameters, IC and DC. Again, you don't like that. Okay? So you want to be in charge of your amplifier. The source and load you usually don't control. I can attach a 10K load, a 1K load, a 2K load. We'll see what that does to your amplifier. But at least you want to make sure that your amplifier stays in its active region, is doing what it is supposed to do. So this is a full circuit, right? So we want to analyze this. I have 2 power supplies plus and minus 3 volts, and everything else is there. So how do I start? Or where do I start?
You go to the lecture slides. There's a formula for this exact kind of circuit, and you just plug in the values and it works.
Bad idea. Because if you learn how to do it that way, I can put a small resistor over here and mess up all of your memories.
Could you do a Thevenin? Like,
Yeah, so I'll go on. But then, what is the starting point? I want to find the gate. That's the final, that's the destination.
You got the operating graph.
I need to do the DC analysis, right? So I start with DC analysis. DC analysis means that all the capacitors are open, right? So I only take into consideration the side that is attached to my circuit. For the source, C2 separates the source from my circuit at DC. I don't care about it. This capacitor, open circuit, I have 2 resistors in series for the emitter, and that capacitor detaches the load from my circuit. So it's a basic common emitter state. We've solved that 100 times. What I like to do is to go and find the Thevenin equivalent of this portion of that circuit, attach it to the base, calculate base current. Right? I'm just going to write it out. So ID is going to be, I can have some V Thevenin minus VBE on, and then I'm ending up into VEE. Divided by R Thevenin plus beta plus 1 and RE1 plus RE2. Or R1 plus R2. Okay? So do we all know where this equation comes from?
no,
Yes, no?
no.
This equation comes from here. So I convert the Thevenin circuit and then attach it to my.
Okay, sure. Okay, yeah, I see it then. Thank you.
So we know where this circuit comes from, right? This one we know. Write a KVL. Oh, it's not ground level, it's VE. Sorry. Write a KVL in here. So KVL tells you VTH is ID RTH plus VDE plus IE R1 plus R2 plus VDE. Okay? So that equation, so I just For IP, I write beta plus 1 times IP, and that's the equation.
In this equation, you mean R1, R2, or R3, and R4 in this case, right?
Sorry?
Well, you circled R3 and R4, but you bring this
No,
up.
no, that's RT.
No, R1 and R2 in the meter circuit, these two.
Well, that.
They're in
Right?
series.
IE times R1 plus R2. The Thevenin resistance RTH is R3 in parallel with R4, and the Thevenin voltage is, this is how you usually calculate it, we can do on the resistance. So VCC minus VE times the voltage drop, the ratio R4 over R3 plus R4 plus VE. So what do? I calculate the voltage drop across the bottom resistor and then shift it by VE because I have two power supplies. Okay? So in this case, I subtract 3 volts from it. VE is minus 3. Just remember VE is negative. VCC is plus 3, VE is minus 3. Okay? So, let's see. Let's calculate this voltage first.
Yeah, it's not.
This voltage is minus 1.8 volts. This is 32 kilo ohms, and I have everything else. For this transistor, I'm using an actual transistor, 23904. I looked at the data sheet, beta is 300, VB is 0.65. This is the same device that you use in the lab. So by plugging those values into that equation, I should be able to find IB. So this tells me that I have a current of 2.02 microamps for IB, and therefore my C, that is 300 times this, is 605 microamps. Okay? Or 606 maybe, if you want to multiply the 300.
No. 600.
That's 606. Okay, so that's IC 605. I need to do what now?
Calculate small signal current.
I need to make sure my device is active.
Yeah.
Okay. VBE, I have no concerns because this is 0.65. Everything seems to be okay. At the base, I have 1.8 volts, right? Almost minus 1.8. At the bottom, I have minus 3. I have enough voltage to turn that guy on. I need to check the base connector, so I need to calculate VC. VC is VCC minus ICRC. So that is going to be 3 minus 0.605.
Oh, I see.
Minus 0.63, okay? I cheated a bit. Nobody caught me, but I cheated a bit. I said VB, the base voltage is minus 1.8. Is it or is it not? It's not. It's base voltage that is the minus 1.8. Thevenin voltage, right? Base voltage is the voltage on this side of this resistor. But the base current is 112 microamp. That resistance is how much? 32K. That voltage is small. So this is going to be more or less 1.8, right? And then the collector voltage ended up being minus 0.63. This is, let's say, minus 1.9. I have a reverse bias back. 1.9 here, minus. And 0.6 over here, minus. So that diode is reverse bias, so I check my active. So active voltage. Okay. Now I go and do my, yes?
Sorry, just a question on the VTH, the one that equates to 1.8 volts.
Yeah.
That formula, where does it come from again? Or that line? Yeah.
This is the voltage drop across R4, right? Because you have 3 at the top minus 3 at the bottom, so that's 6 volts, right? Times the division, the ratio, R4 over 3 R3 plus R4. That's the voltage drop across R4. But I'm measuring it from minus 3 volts, right? So the voltage above it, the open circuit voltage, is going to be that voltage drop above the bottom supply. That's the bottom supply, right?
Yeah.
So V is minus 3, this is 1.2, I guess, adds up to minus 1.8. Not clear? Clear? No?
Just the value, I think, is off by a tenth.
The value of which one?
The 2 microamps. I keep on getting a little bit smaller, a little bit bigger than that, like 20 microamps. I'll double check though.
Yeah, I think, no, because I did the spicing on this, it's inactive. I didn't check all the values, but I think these are okay. I'll have the table, I'll show it to you in a second.
Okay.
Let's just take it, if we make a mistake, we'll go and figure out that. Let's just do it now. Good idea. This is the, so in FT Spice, you can look at the operating point parameters, the command or the Spice directive is .op. It gives you the operating point parameters. So around that, the base voltage is 1.86, we said 1.8-ish. Collector is 0.68, we have how much? 0.65, I think. And then the meter is 0.65 volts, less than that. ICQ1, that's 614 microns. And so we had something not that big, 605, we had 605.
Because he's doing it.
That's it. Okay, so that's that. And then the next thing we want to do is we want to see how this thing behaves. Then I apply my signal, the noise and small signal, yeah. Right? So the hard way that you should do for the first couple of 100 examples is by drawing the full small signal, solving it until you know what it means to have a GNV pi here and a V pi there, and you have a GNV pi here, and the currents how they add up, all that. You have to do that. So do not, so your assignment has a couple of problems that you have to do, a good size small signal analysis problem. Solve more. Solve a bunch of single transistor ones, so that you just warm up. But assuming that you've done that and you know how to draw the small signal circuit, let's just use what we already know. It's a common emitter stage. We know that this stage, if I break it down to this, has these properties. Right? So at the core I have this, but in practice I've attached a few more things to it. Right? So what I do is that I go and try to see if I can reduce that circuit, which I know I can reduce to this, because there is no connection between collector and base or collector and emitter in that circuit. I put this at the center of my circuit and attach everything else that has to be attached to it, and then use what I know, instead of doing the full signal, small signal analysis. So for here, what I do is I draw an AC circuit. AC circuit, what is it? AC circuit means it's not small signal. I'm not drawing a small signal model. But it's how the circuit behaves for AC signals, right? So AC circuit means that the capacitors are shorted now. I just don't draw them anymore. VCC, VEE are ground, AC ground, right? But I don't draw the small signal model for the transistor. So I want to draw the AC circuit. Let's start from the source. I have my R7 here as V source, as R source. This is V source. I do not draw the capacitor. Keep going. So I'm going to see R3 and R4 now. Okay? But R3 and R4 for AC are in parallel. Right? Because R3 is between VB and ground. And sorry, R3 is between VB and ground, and R4 is also between VB and ground. The power supply is ground, AC ground. So I just draw them like this. Okay? Then it's my transistor. In here I have only R1 because R2 is bypassed. And on top of it I have R5 to ground. Then I have R. Okay? So I call this the AC circuit. It's not small signal, it's not large signal, it's something in between. I'm getting rid of all the DC sources in here so that I can focus on the AC performance. But by doing that, I immediately realize or recognize my common radio stage. This is my familiar common radio stage. Right? I just have a resistive divider at the input and a resistive divider at the output. So I'm going to use the formulas I know to get the numbers I need for this circuit. What is the formula? So the formula I have for gain says, if you look at this, so this is V in, we call this V in. It says V out over V in for that stage, for this stage, right? I have a formula for it. It says V out over V in for that stage, for this portion of the circuit, is minus GMRC over 1 plus GMRE. Right? That's the circuit I've analyzed before a million times. RE is easy. V in is applied directly to the base. The only tricky bit here is that what is RC in this circuit? That's for core stage. What is RC in this circuit? What is the resistor in the collector circuit here? There are really two ways to look at it. You can just say it's R5 and I attach RL later. Or you can say RL is already attached. So let's just consider them together. It's going to be R5 in parallel with RL. Right?
Just like
Or you can connect it later. I'll show you what happens if you connect it later. But for now, you can combine them and say V out is just GMRC times, GMV pi times R5 in parallel with RL, if you want to do the small signal analysis. So RC is R5 in parallel with RL, RE is R1, and I'm done. And because it's a common emitter, I always remember that the gain is negative. Am I done? Wanna? Wouldn't it be fun if it was that easy? I know V out over V in. What does the question want? V out over V source. Is V in the same as V source? No. Okay, so how do I find V in?
Is it just
across the R7 versus?
Arsenal. So V in, well, tell me.
Oh,
You could do voltage division from B source across R7, R3, R4
Then what about the transistor?
to find, oh, right.
It's loading that node. What do I do? See, if I didn't have the transistor, my life would be easy. If I just needed to find V in, if this guy wasn't here, that's just what you just said, right? Voltage division between these two. But now that I have this circuit, what do I do?
You have to find the impedance of the rest of that, and then
What I do is I say, I'm going to replace everything I have to the right of it. Is it? Yeah, it is right. With its input resistance, with its equivalent resistance. What is it? It's the input resistance of my common emitter stage. So I can replace this whole thing with just one resistor. Once I do that, life is easy. Two resistors in parallel give you the effective resistance down here, and you just have a voltage division between that and R7. Okay? So, what I need to do, and this is why we talked about that impedance as a load concept. This is where it comes handy. What I need to do is figure out what is this input resistance. I'm going to replace the entire thing with just one resistor in my equivalent model. As soon as I do that, life becomes easy. It's just the resistor voltage divided. So, let me write that down so that I know why I'm doing it. So V in over V source is whatever that R in is in parallel with R3 in parallel with R4. That's the combination of resistors from node V in to ground. And the voltage division is between R7 and this combination. Okay? So if I know R in, life is easy because I have V out over V in, I have V in over V source, I can find V out over V source by multiplying these two by each other. Okay? So that's my plan. And what is R in? R in is 1 plus GM R in times R. Okay? Now all I need to do is go and plug in values into these expressions, and I have this, right? So first thing I need to do is find GM. So IC is 605 microns. So therefore GM is 24 millisieverts. And R5, which is beta over GM, is 12.5 K. Okay? Questions? Good. Okay, so I have those from my DC analysis. I can calculate R in, plug it into here, plug this into here, and done. R in is going to be R prime that I have over here, 12.5 K. And 1 plus GM, that is 0.024. Times RE1, how much is that guy? 200 volts. So this ratio, that GMRE is 4.8 plus 1. So my input resistance is 72.4 kiloohms. Looking into the base. What do I have before it? R3 in parallel with R4, that is 32K. That is in parallel with 72.5K. So let's do the combination and figure out 22 kilohms. Now that I have that, I can find this ratio. So it's the ratio is the combination of those resistors over R7 plus that. It's a voltage division. So it's 22.2 divided by 10 plus 22 by 2. That's 0.69. And then I can calculate my gain. So V out over V in is GM R5 in parallel with RL. So RL is 10K, R5 is 6K. So V out over V in is GM, which is 0.024, with a negative sign of course, times 10K in parallel with 6K, divided by 1 plus GMRV that I have already calculated. So it's 5.8, right? I already have that number. So let's just calculate the this is going to be minus 90 divided by 5.8. That's 15.5 volts per volt. And therefore my total gain, which is V out over Vs, V source, is going to be this number 0.69 times this number 15.5. With a negative sign, of course. Okay. You can go and solve the small signal circuit. You should get the same. But because I know my stage now, I use what I know to make my life a little bit easier. I could do a lot of this stuff really without writing anything. It's easy enough that you can do it in your head. So how do I do that in my head? You have to have an estimate for GM. So GM is about 24 milliseconds. GMRE, if I know it is about 5, then I ignore whatever R5 does in this way. So input resistance, I assume it is GMRE R5, so beta R1. And then do all the calculations relatively quickly from that point on. But let me see, I wanted to come back to a point here. How does biasing affect your gain? So this is actually one takeaway from this, one of the takeaways from this example. So look at how I chose my resistors to establish the desired VTH, 1.8, negative 1.8. I used 40K and 160K. I could have used 400K and 1.6 megawatts, right? Gives me the same ratio. Or I could use 4K and 16K. Again, gives me the same ratio. So at least in terms of the voltage I will have, there is no difference. But with a larger resistor, I would get a little bit more voltage drop across that resistor in my Thevenin circuit, right? That voltage drop will go up a little bit, but it's not a lot of voltage because the current is small. It's a base current, right? So the Thevenin resistance will be 10 times larger if I use 10 times larger resistor for R3 and R4. But this voltage dominates. So the changes here do not affect your IV that much, right? So in terms of biasing, I could do it with all of those combinations. However, if I choose small values for my R4 and R3, so I chose 160 and 40K, the combination is 32K in parallel, right? So if I use 4K and 16K, the combination is 3.2K, right? That 3.2K, when we look at it from the source point of view, is in parallel with the input resistance of this guy. That was large, that was 72K. Now it's your bias resistor that determines your input resistance. That's a bad situation. Right? You want your amplifier to dominate, normally. So you choose these resistors such that the input resistance, at least, if you know how much the input resistance should be, you take these guys into account. It's not just your amplifier that sets your input resistance, it's the combination of these two guys as well. So I choose them such that it doesn't ruin my signal. If these two were 4K and 16K, the ratio between R7 and the input resistance of my amplifier, instead of 0.69, it would be, I don't know, 10 times smaller for this, maybe 0.07, 0.08. I lose most of my signal before it gets to my amplifier. Right? So that's the importance of bias. The other thing is that your amplifier, the core stage, amplifies what it sees. What it sees is the voltage that shows up at the base. You may have a very strong signal here, but if it is coming from the source with a large output resistance, not much of it will get here. Right? So you need to make sure that the input resistance of your amplifier, a typical voltage amplifier, is much bigger than your source resistance. There are situations that we want them to be equal. So like in RF applications, we want them to be equal. Or in low noise applications, we want them to match. But general rule of thumb, your voltage amplifier should have a much bigger resistance than your source resistance, whatever it may be. If you think your source has a 50 ohm output resistance, make sure your input resistance is a few kiloohms. If your source has a 10 kilo ohm output resistance, you want to be in the hundreds of kilo ohm or maybe even mega ohm range. If your source is a capacitive device, which has a very large output impedance, you want to make sure that you may actually in that case not even use a BJT anymore, because BJTs will not give you they give you a lot of gain, but you lose the signal because of the input resistance. It's a combination of the two. How much of the signal gets here, and then how much you amplify it from here to here. You want most of the signal to get here first. That's the first task. Then you want to amplify it. If you lose it before it gets to your amplifier, you may not be able to even recover. Your signal may go below noise. Okay? So I did the analysis on this with the Altius Spice as well. So what is the gain we have here? I actually looked at V in, V source, and V out. So at the top is V in, a 10 millivolt signal, 20 millivolt peak to peak, 10 millivolt peak. Right? V in should be the middle one. V in is the middle one. What's the amplitude? 7 millivolts. What was the ratio we had? 0.69. Right? So you go from 10 millivolts that your source provides to 2.69. That's how much you lost. 30% of the signal you lost. But then you amplify what you got here, and it shows up at the output. So that is the output signal that's about maybe 110 millivolts. What was the gain we had? 10.7. So that had the gain of 10. We have a 10.7. It was about 11, more or less 100, right? And then, so simulation obviously is more precise, but hand calculation we will not have. We are actually very close. Considering the tolerances of resistors, this is as good as simulation. Okay? And we only needed a calculated resistance. Any questions?
The negative sign just means it's out of phase by 180, right?
I'm sorry?
The negative sign just...
Yep. So it means that when the input is going up, the output is going down, and vice versa.
Okay.
Oh, basically, yeah, the negative sign should be here too. Sorry about that. Okay. Any questions? So if you can reduce a circuit to that core stage that we saw before, you can use the formulas that we had. Okay? Those three formulas make your life easy. If you can reduce, sometimes you cannot reduce it to this stage. Let's say if I give you a circuit like this. You cannot reduce this to that. This resistor here is messing up your circuit. Right? Or if I have, I don't know, some sort of a connection between this and it. This is not the same circuit anymore. But in most cases you can. And then if you can, you should use the AC circuit and AC analysis instead of a full small signal analysis. Or you can. You shouldn't. You don't have to, but you can. If you do, life is easy. Okay. Any questions? All right. Do you want to break?